Okay, great. Today we are very happy to have Edgar Dobriban visit us and give us a talk at Silo. And Edgar is currently associate professor in the Department of Statistics and Data Science at Wharton in University of Pennsylvania. And Edgar is actually my academic brother, not only once but twice. Okay, he went to Princeton, where he worked with Jianqing Fan during undergrad, and then he went to Stanford working with Donahoe. So my academic path sort of mirrors Edgar's path. I did my PhD at Princeton, and then spent a few years at Stanford working with Dave Donahoe. Obviously, when I was doing my PhD, we were both interested in high-dimensional statistics, and back then I learned Edgar's great work, in high-dimensional statistics, where he used a very elegant and deep random matrix theory to gain a lot of theoretical insights. As we know, in the past 10 years or so, there has been exciting development in machine learning and AI. And since then, Edgar has been a pioneering figure and published a lot of influential papers on the mathematical foundation of machine learning and AI. And topics include uncertainty quantification, jailbreaking, and AI for math, and so on. Edgar has won a lot of awards, including, I believe, NSF Career Award in 2021, and Sloan Fellowship in 2023, among many other great awards. So today, I guess Edgar is going to talk about some insights and a theory about synthetic data, which is a huge topic right now. Without further ado, let's welcome.
Great, thank you. Thank you very much, Ito, for the invitation and for the kind introduction. I'm very honored to be here. And actually, I gave a Silo seminar in 2020, March. It was virtual. Rob was there. He was asking a lot of, sharp questions. But I'm really glad I'm here in person. And this is probably one of the biggest audiences in kind of an academic seminar that I ever gave. So I'm glad to see so many people. Please feel free to ask questions at any time. I'm happy to, get interrupted. So I'm happy to talk about this topic about statistics. And as we all know, AI is emerging as an important technology. I meant to press this way. Go. Okay, good. So there are large language models, and it's really hard to see here, but this is a Claude Code in action. How many of you have used something like Claude Code or Codex, an AI-assisted coding tool? Quite a few of you. I think there are engineering leaders, saying, we worked for a year to develop something, and then Claude Code did it. It's the same thing, but it was able to do it in a week. So it's kind of just, they're like some of the top, VCs, vice presidents at VPs at Google. They're saying this kind of thing. So I think we are living through some crazy times where the kind of work that we thought, takes a lot of time can be accelerated with the language models. And there are other things like image generation. They can generate graphs, like person riding elephant riding a motorcycle or bike. And there's also the famous AlphaFold, which won the Nobel Prize for being very successful at protein structure prediction. So, and there are all these kind of machine learning things which are all based on the huge amount of data. You feed a very complicated model, and then you get some results. Typically, in statistics for 100 years, what we've been doing is you have a very small amount of data. You work very carefully to write the model, and then you get some something. But now it's a little bit different. And the AI tools are getting so good that they actually can help with mathematical work as well. And I have had some positive experiences with this. I wrote a short kind 10-page just a summary where I describe how it helped some of these AI tools. If you use GPT, it helped me solve a math problem that it's math stat problem that I worked on with PhD students. We worked on it for 2.5 years, and we kind of got some part of it, but GPT helped us solve some of this, helped me solve some of the rest. So I'll talk about this at the end if I have time. But basically, these models are getting very good. And this is a short thing. You can just read it. It's just 10 pages. I encourage you to take a look. I describe my workflow. But at the same time, the AI models, they don't have any built-in guarantees, right? They're not going to guarantee anything. They can make crazy mistakes. So this is just a few months ago, when the GPT-5 came out, people, kind of posted their experiences like, here's a mistake. How many strawberries are there in the word R? It's thinking model, it's the reasoning model, it thinks for a second, it says the letter R had 3 strawberries. That's nonsense. So, initially it was like, oh, they can't count. So they ask the model, how many R's are there in strawberry? So then initially they fixed it. But then it overfit, and now, it's X. So now when you reverse the order, it overfits to it, right? Because initially it was like, how many R's are there in the word strawberry? And it overfits, it somehow makes a mistake. And then also, it writes a lot of code, but it also creates a lot of security problems in the code. Or sometimes you ask it to generate like an image that is the map of Europe, and you can see it's a Mistral model. It's not the best one, but you can see it put Paris here in Norway and London in Finland, and it's nonsense. So again, AI is like I think this is a good way to describe. Sometimes it's great, sometimes it's awful. So and you don't necessarily know ahead of time which one is which. So one particular topic that connects to data and statistics is that of synthetic data. Synthetic data is everything that is generated by an AI model, okay? And this is a random paper it's a random paper from Nature Communication that I took a screenshot where people say, hey, I will use AI generated synthetic data of X-ray, chest X-rays for stuff. Like I will ask the model to generate a healthy radiograph, radiograph the pacemaker, no pacemaker, and the effusion, and so on. And then I take this data and I augment my current data and I use it for educational purposes. I also use it for testing, for training models, for share it with my collaborators. So, but we just saw that it's sometimes great, sometimes not so great, right? So how can we trust this synthetic data? How can we still use it in a safe, reliable way? So that's the question that I'm trying to address. Okay, and this area is just emerging in statistics. There's a few papers. I'll mention here one from Shihong Lin. Shihong Lin, she's a leader in biostatistics at Harvard. She has this paper where she uses synthetic data in genome-wide association studies. She and her team, they developed the kind of model that if you have real data and synthetic data in genome-wide association studies, synthetic data means like other GWASs. Somehow you can connect them together and get better prediction. There's another paper here from UCLA, Guan Chen's group. They also have a utility theoretic perspective. So I will have a different perspective, and but still roughly the same goal. That how to use this synthetic data in statistical inference, where we know that we care about type 1 error control, we care about confidence interval coverage. We have all those things that we know and we like, and we want to use this imperfect synthetic data. So this is a collaboration with Professor Yannick Romano from Technion. Yannick has some great students that work on this project, Neshi and Roy, and there's a postdoc at Pan Yong-Hoon who I co-mentor with my colleague Eric Chadgan, and we co-advise him, and this is the team for this project, and I'm happy to talk about it. So what kind of an overview, what I'll do is I'll present this method that I call GESPI, General Synthetic-Powered Inference. So this is a method that you can think about as kind of a wrapper that it's a tool that can address it can solve a broad class of statistical inference problems. Using synthetic data, it leverages the synthetic data to make the inference better. I'll have to explain what that means. It somehow combines the real and synthetic data. And it can handle, it's general, it's based on some loss control perspective that I'll describe, but because it's so general, it can address hypothesis testing problems, prediction sets, conformal risk control, multiple testing, and we show a bunch of applications to evaluating LLMs, meaning testing win rates for LLMs, interpretability of LLMs, protein structure prediction, and some outlier detection as well. So it's kind of a general framework that we propose, and despite that, it's very simple. And I think there's a lot to it, and also a lot of follow-up work that we're also working on. So let me tell you kind of a little bit more about the formal setup that we consider. So we look at kind of standard statistical decision theory perspective. We have a loss function, okay, like WALD, in the 40s, basic loss function in decision theory, and we want to control a risk measure, which is the expectation of the loss, okay, over the population. But we don't have the population; we just have data, okay. And we consider a setting where, in fact, we have some data. And z is kind of a generic data point. Z to infinity means that the algorithm works for 3, 4, 5, any number of data points, okay? And we have this algorithm, and whenever you input a data set dn from the real distribution, you pass it through the algorithm, and you evaluate the loss of that result, where you also allow an additional test data point, potentially, optionally. This is kind of optional, like a test data point, if you want to predict a future data point. Then we consider a setting where it is possible to control this expected loss, which is the risk, at level alpha. So we assume that it's possible. And you're like, oh, it is really possible. It is possible in many cases. Let's consider, for instance, hypothesis testing. Okay? In hypothesis testing, what you're doing is just a binary decision. You either reject the null hypothesis, meaning you don't believe that your model is consistent with the data, or you do not reject the null hypothesis, which means that at the moment you believe it's consistent with the data. Okay, that's basic hypothesis testing. You either reject the null or not. Then the loss function is just the loss is just phi, meaning the loss is just still binary loss. And then what is this quantity? In that case, it's just going to be the expected value of your indicator of you reject or not. That's exactly the type one. So there are many settings in statistics where we figured out how to construct an algorithm that can, in fact, control the type 1 error at level alpha. There are some questions? No. Okay. Please ask questions and say I have questions. Right? They might not see everybody or have another question. Oh, please.
Could you explain again the two P's there? So the capital, the cursive P and the normal P.
So this one is the data distribution, which we don't know. We just have a sample from it. Okay. And this one is the set of distributions in the null, let's say. It's when you write down a null hypothesis, that means you specify a set of distributions that you think that's my model, that's my kind of null model for the data. It could be just one distribution, but here, for instance, it's all the null distribution.
And then the expectation is over that T, which means the D is sampled from the
exactly.
Yeah. Okay.
The D is sampled. Let's say the DN is an IID sample from the 20.
Okay.
But it can be other things as well. We'll talk about. Okay. So, but there are other settings that we can also handle. For instance, in the kind of popular area of conformal prediction, what is this algorithm? The algorithm is a prediction set. So what happens is you have a bunch of data points, and then what you do is you construct something that when you predict that you get an input image, let's say, you output a set of classes. You don't just output, I believe this is a building. You have a list. I believe this is a building, a vehicle, a plant, or an animal. Okay, I have a list of classes. The C hat is a set. And what I do is when I have a test data point, xn plus 1, minus plus 1, there's the V, test data point. Then my loss is binary, and it is 1 if my yn plus 1 is not in the prediction set. So what I'm trying to do is I'm trying to predict the next data point, and I want to ensure that it is in the set. Okay, so it's like you might be more familiar with the notion of confidence interval, where the only difference is that what you're trying to predict in the confidence interval is not the future observation, but rather the never observable parameter, right? That's the more standard thing. But this is kind of now emerging, and it's motivated again by ML, where you have very accurate predictors and you're trying to predict some. So that in this setting, what happens? What does this belong? What does this become? I claim that this belongs to coverage error, namely the probability that y is not in Cn plus C of x hat, C hat of xn plus 1. Why? Because this probability is just the expectation of this indicator that y(n plus 1) is not in CLN plus 1. So the expected value of the loss right here, you see, it's exactly the coverage error. So what's the upshot here? We consider this general setting, but if we know how, if I tell you how to use synthetic data in this setting, then I have also solved how to use synthetic data for hypothesis testing, for instance, and also for conformal prediction, and actually also for confidence intervals and other settings. Okay, so I will do the more abstract I will work at the more abstract level, but all that also is relevant for these kind of special, more concrete problems, which are kind of stat 101. They're more like standard stats. Any questions on this setting? So far, I haven't told you about synthetic data. This is just like the kind of the type of formulation that we look at. No questions so far. Okay. So now, assuming that we can do this, how do we use the synthetic data? And what can we hope for? So in addition to that dn, now we assume that we have some additional data, that's this d tilde, and I write this lower, capital N here to indicate that it's somehow larger sample size. So it doesn't have to be necessarily larger, but this is just kind of evocative that this is kind of larger data set. And I want to consider this. I want to develop an algorithm that I call L tilde that uses both the real and synthetic data that quote unquote somehow improve this real only algorithm. Okay, I want to combine the real and synthetic data somehow together in a way that helps. So how can I do that? And what do I want? So there's many goals, but in this formulation, what I want is if the synthetic data is of high quality, it's good synthetic data, then basically the resulting algorithm should work as if I just have more real data. That's the dream goal, right? Generically speaking, the best thing to do for the synthetic data is to be more like the real data, right? So if I could have more synthetic data that is more like the real data, and if I could imitate this algorithm, that would be great. But there's a problem. If the synthetic data is bad, it's low quality, then what do I want? Then I want the algorithm to not use this synthetic data too much, right? Because if using it too much, then my algorithm is going to lose the risk control, is going to behave poorly. Yeah. So then, if the synthetic is bad, then I don't use this. So somehow I want two goals simultaneously, and that's exactly what our algorithm will do. And it turns out one of the main difficulties is that ahead of time, we don't know that well how good the synthetic data is. And especially, we may not ever know it very well because we assume we only have, let's say, 10, 15 real data points. So it's hard to estimate how good even though I have 1 million synthetic data points, I only have 10 real data points. So I can't really evaluate that well how, I can't run a goodness of fit test and I hope to get some power or something like that because I only have very little real data. Yes.
Maybe you'll get to it, but I'm just kind of struggling to match up to your definition of risk control here. Now, is P going to be over like all couplings over dn and d tilde, or like are we?
It's going to be some TV distance something.
Okay, so you are going to have to think about the distribution of your synthetic data.
Yes.
The true.
Yes. Okay, and so, roughly speaking, as a cartoon here, what we will do is we will run our algorithm as usual, and we will also run an algorithm that combines the real and synthetic data together. But then, as a key additional thing, we will also run a guardrail algorithm at kind of a more relaxed level, and somehow these three will combine, and this will give us the inference that we want. And this is just a cartoon, but I will describe the details, here. So. Now, again, because we did it a little bit robust, a little bit generally, this is going to be a little bit abstract here. But let me try to motivate it for you. So, in our perspective, we want to be robust. That means small loss. We want to do well, right? Small loss is good. Okay. So, in order to do that, we need to be able to compare actions. Remember, the algorithm outputs something. I didn't say that, but the algorithm outputs actions. The action is kind of more general than an estimator or a test or a interval. We view them as actions, okay? We want to be able to compare actions in order to choose the better one, which has a lower loss, okay? So now to do that, because we want to do things abstractly and generally, we will introduce this notion of the action space, which needs to be partially ordered at least, so that for any two actions, the minimum of the two actions is well defined. So for instance, I have two intervals. What is the minimum? Is the union of them. Why? If I have two intervals and I take the union, that is definitely going to have a smaller loss, right? Because my parameter is more likely to be inside the bigger interval. Okay, so big is good actually, yeah, for intervals. Bigger interval has smaller loss. So here the minimum for intervals, it will be the union. Okay, and notice that intervals are not always comparable. Like if one interval is in another one, then it's hard. If one interval contains the other one, that's better. But not all intervals are directly comparable. So that's why it's a partial order. And also the loss is monotone. So to kind of transfer this to the loss. So just look at examples. So like for a confidence interval or prediction interval, it's one interval is better than the other if it contains another interval, and the minimum is defined as the union. And the same thing for the prediction set. One interval is include like one prediction set is better than the other one if it includes the other one, and the minimum is the better one is defined as the union. So this is a little bit abstract. So if you want, you can just think about the confidence interval problem or the predictive inference problem, and you'll get most of the ideas. For hypothesis testing, when you have a 0-1 action, what is the ordering? If I don't reject, I make fewer mistakes, right? So I have a smaller loss. So then A1 is better than A2. So the 0 is better than 1. Because if I don't reject, then I have a smaller loss. Okay. Any questions on this formulation? It's a little bit abstract, I know, but this is the way we found out that we can, we could write a separate paper for confidence interval, a separate paper for this one and this one, but actually, in fact, we did write the first paper about this one before we did the predictive inference, which was probably the newest, until we figured out, hey, you can actually do everything with the same idea. Okay.
Can I ask a quick question? So the partial ordering of action space, does it actually meaningfully restrict anything in the, like if you wouldn't have it versus you would have it, is there anything you're losing there?
We just need to know what is the ordering. Yeah, that's you can have any action space. You just need to also you just need to give me the order. Yeah, you need to give me the ordering, partial ordering. Yeah, and especially you need to give me the minimum. That's very important. Okay, now suppose that we have this algorithm that controls the risk at level alpha using the real data. What are we going to do? Very simple. Okay, simplicity is helpful. So what we're going to do is we're going to run the algorithm at level alpha using both the real and synthetic data together. So that's very good if the synthetic data is high quality, okay? But what if the synthetic data is bad? And it's not going to control the loss. So then we need to take the minimum to control the loss, to pull down the loss with something else. What can we do? We can run the algorithm at a slightly higher level with just the real data. If we just run it at level alpha, turns out usually this will be smaller. So this will basically you wouldn't use the real, you wouldn't use the synthetic data at all. So you need to pay a little bit of a price. This epsilon is kind of like the price of using the synthetic data. You pay a little bit of a price. You inflate your type 1 error in the worst case, and then you're allowed to use the synthetic data. And I will go through it carefully step by step to to explain this in more detail. But this is not a definition, and I simplify it. I think we'll have a more complex setting in a second. But basically, I just run the algorithm using the real and synthetic data at level alpha. Okay. And I run the algorithm on the real data only at level alpha epsilon at a higher level. Okay. So epsilon is kind of like the admission cost. Like, do you want to use synthetic data or not? Turns out, if you want to use synthetic data and you're not willing to change your alpha, the worst case optimal thing is to not use synthetic data. We actually have a theorem about this, that the only way to not increase your error in the worst case, because synthetic data doesn't, real data is here, synthetic data is somewhere here. If you insist that you don't want to increase your error from alpha at all, the only thing to do is not use the synthetic data, because it could be here, it could be here, it could be here, it could be here. I don't know where it is. So the only way to use synthetic data and benefit from it is to increase your alpha a little bit. And you decide how much you want to increase in the worst case. Okay, so just to reinforce this, if the synthetic data is similar to the real data, then basically it's going to be this one. Turns out that comes out to be the choice among the two choices, the value of this one and this one. And it basically it's going to be like running the algorithm with a larger sample size. And if the synthetic data distribution is different, it's kind of, this distribution, then this can go up to infinity, but this one still stays. So we will use basically this one in the worst case. Okay. The second, the second one. Okay. So I will go through more examples and definitions. Yeah.
There are there is
Okay, so turns out the source of the synthetic data here, it can be anything. It can be from prior historic work, historical data set, and turns out our theory accommodates any dependent structure. Like you can generate the synthetic data based on the real data, and that is allowed. And our first of all, the algorithm is well defined, but also our guarantees will hold if you just calculate everything accordingly. So that turns out it's robust. My ideas. So abstract and so general that's allowed. I'll show you in a second. Okay. So now That's fine. So I'll just continue here then. Great, let's return.
Yeah, the
Yeah.
Zoom audio is good. Can I ask a question though from Zoom?
Yeah. Okay.
Could you please go back to the previous slide? I just want to get the intuition of the minimum action. So if I think of the algorithm as producing a confidence interval, let's say, is the alpha plus epsilon dn interval wider?
That depends on the real data and the synthetic data structure. Yeah, but the alpha plus epsilon interval is definitely, I mean, what it's guaranteed to do is guaranteed to have 1 minus alpha minus epsilon coverage. So the coverage is actually like instead of 95%, 93%. So actually, it's not wider, it's the opposite. And the minimum is the union. You take the union of a less wide interval. Yeah. So basically, your worst case coverage will go down to 93%.
Right. I was trying to get the intuition like, would the second term, the alpha plus epsilon term, kind of wash out the benefit of that synthetic data? I think I got the intuition in the reverse direction.
It's not a wider interval, it's a smaller interval.
Okay, thanks.
Okay, yeah. So anyway, so just like you would expect, because you take the minimum, the loss is bounded by the minimum of two things: the alpha plus epsilon, the worst case, and alpha plus dp2, which dp2 is basically a total variation distance between the outputs of the algorithm when you run it on real and synthetic data, roughly speaking. So that means that if the real data somehow is close to the synthetic data, then your distance is going to be 0, and you're going to control the risk at level alpha. So that's good. And in the worst case, you're going to control the alpha plus epsilon. But there's something missing, which this just shows in some sense that the algorithm doesn't do worse than alpha, right? Because I can only control the interval the loss at level alpha just with the real data. So this just shows that this doesn't increase. So what we in addition have experimental, we don't have to hear about it, but we also show experimentally a bunch of benefits, including turns out that this loss has a variance reduction. The variance of this loss reduces in the experiments, and so there are additional benefits that not shown here. That basically this is helpful. Okay, so if again P is Q, then you have risk bounded by alpha plus all the other benefits like some variance reduction and so on. And if this Q is large, then you still get the risk bounded by alpha plus epsilon. So that's the set. Yeah. So actually here, forget about this. So no, because turns out this dpq is just that whatever distribution there is on d and d tilde, that will be reflected by the dpq, the total variation distance under that sampling. So whatever the real data can depend on synthetic data can depend on the real data, and then as long as you write down the dpq, the total variation distance for that, then it's correct for that.
Yeah. The Q is kind of dependent on D in its track.
It can't be dependent on P. Yeah, that's fine. That's allowed. That's allowed. Yeah. Okay, and then you know what? Yeah, I actually just for this. So the other thing is that so this is the better of two actions. What the better is take a union of intervals. So you can easily get a bigger interval, and you're always going to get a bigger interval, but you get a very large interval. And in order to ensure that that doesn't happen, we have an additional guardrail on making sure that we don't get too big. So we need to take basically the worst of some action, and we have the thing that I talked about in the previous slide, and the maximum of just the usual algorithm at level alpha. So basically, you take the intersection of this interval, of this union interval, you take the union of these two intervals, and then you take the intersection with this interval. And that way you make sure that you never have, you never get too large, because you take the intersection as well. Yeah, and we have similar theorem, but for that one, but just as a kind of obvious thing, is that this thing is in between the 95% interval, it's included in the 95% interval, and it includes the 93% interval. Okay, it's in between those two things, And it also has this variance reduction and benefit from the synthetic data. So let me show you some experimental results to kind of get a sense of, what, yeah. So, okay, first of all, just, this is a pattern, like, you take the union of two intervals, synthetic leveraging guardrail at level epsilon, which is, smaller, and then intersect with this one. For hyper testing, it's kind of and or pattern, and for multiple testing, it's something like this. So now, hopefully, yeah. Okay, so, yeah, so here's a example about conformal prediction sets or prediction set with some risk control. So I already mentioned this one to you. There's an expansion to so-called conformal risk control in the paper by Andrew Polos and collaborators few years ago, where they try to basically develop an analog for the case where you want to control some loss, and that's what we will show you here. I will show you here. This is how the prediction sets look like. I already mentioned this. They're included like this, and it's it basically our method has width no greater than the C hat. This one because it's an intersection. The mid coverage is always less than epsilon because of this one. And let's see the example. So standard image classification example. We want to construct a prediction set for labels, prediction set of labels for unlabeled images. Really, the image is actually a very large data set, right? But turns out we can ask for strong property, not just marginal coverage, but class conditional coverage. For every class individually, you want to have 1 minus alpha coverage, and then suddenly your data gets divided by, let's say, if you have 1,000 classes, the sample size gets divided by 1,000 because you also, you don't have that much data for each class. So we can ask for a strong property called class conditional coverage. Okay, and then we have the synthetic data, which are these, diffusion model generated images by flux. So this is how a real golden retriever looks like. And these are some synthetic golden retrievers. And you can see they look very similar. But in the background, this background is kind of like you can see the little bit here, the more of the background. You can see the fence in the background. Here there's no fence, right? So it's still a little bit different. And we do it for 30 classes, including like this one, white wolf and the beaver, and so on. So, okay, we run our method, and here's the results. So we have 15 data points for every of the 30 classes, and we generate 1,000 synthetic images. And we want our coverage at 95%, that's alpha 0.05, and the admission cost we're going to pay because synthetic data is 5%, is 2%. So here's how the results look like. So if you just run the base method for each of the classes separately, you get coverage equal to 1. And what does that mean, coverage equal to 1? It means that you always output 30 classes, 30 classes, 30 classes. So the prediction sets are not informative. At every image, you predict all of the 30 classes every time. That is completely useless. And we directly chose it to be like that because conformal prediction, just like a permutation test, the best coverage that if you have 15 data points, basically the coverage that it can get is in multiples of 1 over n plus 1. So 1 over 16, 2 over 16, 3 over 16, 15 over 16. That's the biggest coverage that it can get to be non-trivial. 60, like to get 95% coverage, the only way it can do between discreteness is to get full prediction sets. The conformation fails here. It's useless. Okay. Now, what happens if you just run the synthetic only data? What happens? Well, if you look here, you get 60% coverage. Why? Because it turns out the real data and the synthetic they are different. There's no reason that you should get coverage. It's different data, right? No, for some other classes, it turns out it gets better. Like for instance, you get the magpie. It's kind of above our this red line is the 93%, the guardrail, and the black line is the 95%, the true target. And we here for instance for this class it works better, but it turns out for some of them it fails, right? So simply on its own it's not reliable. You can't do it. You can use it, but it's not reliable. Now what happens if you run the so-called guardrail method? What is the guardrail method? The guardrail method is just this one. You can say, hey, I'm going to enlarge my level to, instead of 5%, I'm going to have it at 7%. What happens if you just run that one? That is, because we are always less powerful than that. So you might even say, oh, why don't you just run this one? It turns out it does achieve the 93% coverage everywhere. Here, it always achieves it. That's the red one. But it turns out it can have a pretty high variability. Whereas finally our solution, our method, the GESPI, okay, that one always is above the red line. It always achieves the desired target level coverage. Yeah, and it has smaller variance. You see the variability here? Much smaller than this one. This huge variability, small variability. Same thing. So it's better than the red one, better than the red one. And here it doesn't have any benefit, it doesn't have any benefit. But so basically, here on these classes, it has benefit because it has smaller variance. Here on these classes, it has variance because it achieves coverage. Okay, so it's kind of people maybe imagine, oh, there's some alternative where you can do this, you can do that. I don't really know. I think what we did is roughly the correct thing, or the correct thing to do. And in terms of sizes, if you look at the sizes of the sets, like here, because the synthetic only fails, you have to do larger sets. So we have larger sets than GESPI has larger sets. That's you need to get coverage. Yeah, question.
You can go.
Yeah.
Can you explain again what happens if you don't pay enough with the epsilon? Like if you did epsilon 0.01?
If you
like how did you choose epsilon?
It's gonna be very similar to this. It's not a big deal. Yeah. Maybe if you put epsilon to be too small, basically the GESPI might become essentially the same as the beta, because it's sandwiched between the two. So that might, if you don't pay enough, basically you're also not going to gain anything from the synthetic data. Yeah. Yeah.
So if I only look at your coverage, it's somewhat of a unsatisfying story, because your sort of use synthetic data and made your coverage worse. But is really the salvage here that you only have good coverage for the base method because your set is so large?
Yeah, absolutely. I mean, the only way to achieve coverage with the 95% with this, which is huge failure. I mean, I have to output 30 classes. Yeah.
I see.
Exactly. So basically, you think it through carefully. This one, and this one alone, they don't work. But if you combine, our method is really the combination of the three. Combine it the right way, you kind of get a little bit of a better kind of Pareto curve.
Somehow you're just improving the bias.
And also reducing the variance simultaneously. Both of those things. It's a better bias variance. Like, I guess you could say that these are, this is hugely biased and this is hugely variable. Yeah. And we kind of really, and the thing is how to interpolate. And if it was an estimation problem, we discussed this at dinner last night. If you had an estimation problem, you could just take plus and weighted averages. But here, because they're sets, what's the weighted average of a set or something like that? So you really need to take this kind of union intersection. That's kind of a little bit harder to think through. Yeah. Okay. Anyway, and we have a bunch more examples. They're all similar. So I have maybe I'll just flash something about protein structure prediction. So here we're trying to basically what we're trying to do is so AlphaFold gives us a prediction, something, of a protein structure. And what we're trying to do is label the parts that are accurate and label the parts that are not accurate. So the real structure is here. And when you look at it, these helices, they're not doing that well, compared to the real ones. They're not very, accurate. The sheets are pretty decent, but the helices are not. So what we want is just kind of have this labeling, it's like color coding, where this is bad, the red is bad, and the blue is good. Okay. And so what we can do, so of course, what you want to ideally you want to label the precise ones that have a large error. But at least you should not label too many red ones if possible, right? If there's only like a small number of errors, you shouldn't label too many errors. So that's actually what the standard methods end up doing. If you just use the real data, it's basically going to be all red. It's going to label everything as an error. So that's what we achieve here. Basically, the base method achieves which is conformal risk control. Here, it achieves good risk control, but it abstains. Basically, it labels 60% of the protein as an error. So yeah, you look at it like, oh, everything is error. So our method manages to reduce it not that much, but to 45%, something like that. And we also have a smaller variance. And if you use the guardrail, of course you reduce it also to 45%. But that's the guardrail should do that, but it has higher variance. So that's kind of the story that we are able to. It's kind of like a very tricky bias variance trade-off here. Okay, let me skip this part on hypothesis testing. We have multiple testing. We have theory for two-thirds GESPI. We have a lot of, and we're kind of writing follow-up papers as well. So this is the summary of the main talk. So I developed this method GESPI, kind of a method, this method to leverage synthetic data for statistical inference. It's going to be good, helps when the synthetic data is similar to the real data, and it always satisfies the guardrail. So you can use it with reliable, you can trust it.
So is there any way to kind of quantify this variance reduction in terms of that distance between P and Q? Like, I guess that must track somehow, right?
We are still trying to figure that out. Yeah, it's a very good question. It wasn't so easy for us. It wasn't. Yeah, we don't have any results yet.
Distance small, the variance reduction would be more than if it's large, then it's basically no variance reduction relative to the I guess.
Yeah, that would be the dream. I would love to be able to prove something like that. Yes. Yeah.
But you don't even know if it's monotonic.
I don't know if it's monotonic. Yeah, I have no idea. Yeah. So there's another question online. Let me just finish this slide. There's also a question of how to generate synthetic data if I want to use this, based on can we use it to generate. And we have actually not a preprint. This one, I know it is a preprint. The previous one is Nurip's paper. This one is still a preprint. Thank you very much. There's a question, Jerry.
All right, thank you very much for the interesting talk. I have two questions. The first one is, I notice your guarantee assumes the synthetic data is drawn from a distribution, and it's the kind of like a distance between those two distributions that quantify the usefulness. I wonder if there is a way to have a kind of like an empirical version of this, where I have a synthetic data set. Like I didn't draw it from some distribution, and who knows, it may not even be ID from something. Like I just don't know, but I have that. So what can be said, if anything, about in that situation?
Good question. I don't know, but what I would say is that if you generated the synthetic data based on the real data, that induces a distribution. But I don't know the answer to your question.
All right. The second question is, at the very end of your talk, you hinted at optimum ways to generate this synthetic data set. Is there anything you can reveal to us? What's the key idea there?
Yeah. So it's actually reusing that same idea that you can generate, like our algorithm works, or it applies even if you generate the synthetic data conditional on the real data. So that's very powerful. Turns out here we just looked at the coverage, which is kind of like, you can make the coverage small, but then you make the length large. So it turns out our current idea, it's an ongoing project, is now you consider both objectives simultaneously, and then you kind of try to train a generative model to minimize the length subject to satisfying coverage, and you get some Lagrangian, something like that. Yeah.
I see. So it's based on the empirical, the real data set that you have. It's not, you don't know the distribution of it.
Yes.
All right. Thank you.
Great. Well, thank you very much. If there's a few minutes at the end and you're interested, I'm happy to talk to you a little bit about the statistics with AI. I don't know if I have a few minutes at the end. Yeah. Okay. So what I would like to talk about then is this kind of AI for statistics. So let me tell you a little bit about kind of the context of this problem. This sounds like a different talk now, right? So I wanted to solve this problem. I proposed this problem to my PhD student about the robust density estimation under Wasserstein contamination. So more specifically, kind of math that, okay? I have an IID sample from a p-dimensional real valued data with some density f that's S-Hölder smooth. This is standard non-parametric smoothness, okay? And I want to estimate f at a point. Okay, this is a kind of standard non-parametric statistics. But now I don't observe the original data because there's some contamination, there's some distribution shift, there's something, okay? And this contaminated sample, the x1 prime up to xn prime, that's what I observed as IID from some other distribution. And there, what we assume is that the boundedness is in some optimal transport sense, the Wasserstein distance between the two distributions, that the real one and the third one is again bounded by epsilon. The epsilon comes up again, different epsilon here. So basically what this means is there's a coupling of the original, the real data, and the observed data. That's of that's the difference, the LQ norm of the R power difference doesn't matter. So usually what people do in Wasserstein is just L2 norm. And if you hear, oh, Wasserstein R, that means L2 to the power R. Usually it's a Euclidean one. So question is what to do here, how to estimate the data here. And so I proposed to my student in February 2021, and we worked on this for 2.5 years. We worked very hard on this. And what we were able to prove is that the minimax optimal rate, when you have any epsilon, any smoothness, and in fact, we were only able to handle the one-dimensional case for W2 perturbation, so L2 norm to the power 2, and we show that it's between two bounds, two things. This is the usual nonparametric rate, okay? This is the usual n to the minus 2s or 2s, so that's the usual textbook nonparametric rate, and some function of epsilon. And the thing is, the epsilon powers, they don't match. You see it on like 2s, s plus 1/2, 2s, s plus. We couldn't fix that. That's what we got, that's what we got. And then, my student graduated, so our paper got a revision. Somebody has to do it. I have to do it now. It's done. It can open AI, doing well, but I have to do it. So I went to scientific, and in basically 2 months working, I was able to get the optimal rate, not just for this special case, but for general P, Q, and R. And I was able to show that it's this much, the same 2s over 2s P is here, but more general because it's more dimensional. And this is the right power of the epsilon. Okay. The right power is this much, and then if you calculate it, you see that it's strictly in between them. So our previous upper bound wasn't right, the lower bound wasn't right. So but more interesting is what so first of all, why this is interesting is because this forms an intersection of classical statistics, density estimation, robustness, and optimal transport. And when you think about who is there one person in this world who's an expert at all these three of them together? I don't think there's any expert at all three of them. I don't know about them at least. But the AI can help you. When I know a little bit about this. I know less about this and even less about this. I really know at least one book in every topic. But so that's why the AI is helpful. So for the lower bound, let me just give you an idea. You kind of have to use kind of a modulus of continuity, which kind of just how much is the distribution perturbed by this epsilon perturbation. That's what you kind of have to use. But we use this so basically you have to bound, like if you perturb f by f to f filled by epsilon, how much does this change? Yeah. So and we use the Telegram transportation cost because that's all we knew. We use the Telegram transportation cost inequality. It turns out, what does GPT suggest? I basically copy paste the prompt, copy paste the entire paper essentially, and ask it, can you improve the upper bound or lower bound? It thinks, and then it tells you, hey, there's something, it's not sharp. This bound is linear, but it should be quadratic. And it gives you the correct strategy. What you should not use the Telegram, you should use a dynamic Benhamou-Brenier PDE formulation. And I didn't know about that, but I was able to check it's correct, and it gives you a better bound. Okay? And then, now it's very sharp. I mean, it's very fast now. But okay, the Benhamou-Brenier dynamic formula, and it gives you the proof. Well, and then of course I checked it very carefully. I found the references. I checked it very carefully, and this gives you the correct bound, and it closed our lower bound. The upper bound also was like this. So anyway, the main message is here is if you haven't used these methods, I think you may be able to benefit a lot in your research. I mean, I think this is a to me it's I'm very happy that I was able to get these results, and I wouldn't be able. It would take me much more time to do it without the help of these tools. So that's just something. That's just something that I want to convey here. Okay, thank you very much.
Right.
Any other question? Yeah, let's take the questions offline. Thank you.
Thank you.